Hello. Before we jump into Unit 8, I have a message from your teacher. That's me. The year's 2025, and I'm refilming these videos because the ones I made during COVID were pretty rough. The audio is pretty difficult to listen to. But here's my message to you is that as we approach the last 2 units of the year, I really need you to lock in. If you have developed any bad habits, for example, if you have developed the habit of just writing down what I write down without listening to the preparatory lesson, without thinking about it, without reading the text for yourself, those habits are not going to serve you in these last 2 units. So I need you to pay attention. I need you to write down what questions you have. I need you to stay engaged. That way we can make the most use of our 94 minutes together each class time and use that time for more engaging problem solving than me lecturing to you in class, which I don't care to do very much. So all of that to say, here we go. Unit 8 is going to get pretty tough pretty quickly, but you've got this. So just don't get behind. In section 8.3, we're working with differential equations and slope fields. And I'm going to note that differential equations are nothing new because they are just equations that involve a derivative. So for example, the y double prime minus 3y prime plus y equals 0, we call that a second order differential equation. Since it's a second order derivative, we will mostly work with first order differential equations, meaning they involve y prime or dy dx. So something that we will do lightly in Calc AB is we will solve differential equations, and that means to find the function y equals f of x that solves the equation. I just want to note this is really similar, a very similar process to finding an antiderivative. So we know, for example, that if we integrate some function f, that we could get infinitely many antiderivatives f of x, so we always write that plus c, so that allows for different constants of integration. However, we're going to work on solving specific or particular solutions to differential equations, which means that we will just have to find what that c, what that constant is, because again, otherwise they're ultimately infinite solutions. Okay, this first example, show that y equals e to the power of 3t, show that as a solution to the given differential equation. So that might seem confusing at first, but when I unpack that, it just involves the derivatives of y. So if y is e to the 3t, I might start by finding y prime, and just using the chain rule there, I get 3e to the 3t, and my second derivative, the derivative of y prime, will become 9e to the 3t. So if I look at this equation, well, let's just plug that stuff in and see what happens. So our second derivative, 9e to the 3t, minus 2 times our first derivative, I always substitute into parentheses, equals 3 times y, and we know y was e to the 3t. So to show, like you might see it right now, that this is a solution, if we're ever asked to show mathematically that something's a solution or prove that something is a solution, we really need to get to a place where our left and right side of the equations are the same. But when we simplify that left-hand side, we can see that it matches the right-hand side. So we have shown that y equals e to the 3t is a solution to that second order differential equation we were given. So a lot of the applications of differential equations are times in life where we know information about a rate of change, but we know less information about like the quantity of changing. I think this comes up pretty often in the medical field. For example, the rate at which medication is absorbed into the bloodstream. From that rate, we can inform ourselves of how to prescribe and like quantify doses of medication. So, all right, slope fields. So a slope field is shown below in a three-dimensional space, like that you would study in Calc 3, you would learn about force fields, which is kind of like a three-dimensional slope field. So slope fields are visual representations of the multiple solutions of differential equations. So again, I want you to read this whole text up here, but when we consider this slope field, we use the slope field to visualize the graphs of the solutions to a differential equation. So the differential equation that we're viewing the slope field for is the differential equation that dy dx equals x plus y. So basically, any solution to this differential equation at any point along its curve, it's the slope of its tangent line, or its slope, if it is in fact linear, should be x plus y. Okay, so if we look at our table over here, this table is something that if we're ever making a slope field, we're going to create this table for ourselves. But this table is some different y values and x values, and we could see where, like in the graph, for example, these points are represented. So like when x is -3 and when y is -3, my slope is 0. Well, if I look in the slope field where x is -3, or sorry, where x is -3 and y is +3, that would make a lot more sense, huh? If I go up to that spot in the slope field, it's about here, and you might notice this like kind of this path where all these little line segments right here appear to be horizontal. Well, all those little line segments represent a space where we would have a slope of 0. So we could see, like in our table, all of these zeros. That's going to be where we observe that in the slope field. So what we're going to do real fast is we're going to look at 3 solution curves. So let's look at the ordered pair, or the point 0, 2. So again, this slope field is letting us visualize multiple solutions to this differential equation here. And this is not a separable differential equation, so it's not one we're going to learn to solve in our class. But if I want to visualize this, if I go to the ordered pair 0, 2, I'm going to put a dot right here, a point rather. And what I can do is on the going to the right and the left of that point, just kind of follow the slope fields, like almost like it's a current that you're getting kind of trapped in. So here I see to the right, it gets steeper and steeper and steeper. On the left-hand side, if I go, it kind of gets shallower, and then I get to that spot where my slope is 0. And then I kind of get caught up into like this. It feels like I'm stuck in a current as I go backwards. So the curve that we just sketched, this represents the this represents the solution to the differential equation. Some y equals, like, I don't know what y equals, but 0, 2, that ordered pair would be a solution to that y, and our dy dx would be x plus y. I know it's kind of a lot to think about at first. All right, let's look at 2 other possible solutions. So if we go to the ordered pair -2, 0, so just right here on the x-axis, if I kind of follow those little slope field curves, I can see I'm just going to get pretty steep pretty fast in this direction. As I kind of go backwards, I'm kind of following the current. I think I'm going to kind of get caught up in about the same spot that I did before here. So again, this curve is another solution. It's another y equals, that would have this derivative, dy dx, and the ordered pair -2, 0 is a solution to it. All right, so finally, if we look at just one more, let's look at the point 3, -1. If I find my point at 3, -1, that's about here-ish. Sometimes on the AP exam, we have to sketch these slope curves. I don't know if we will this year since they're moving to that like digital format. I don't really know what's going to happen. We'll find out in May. All right, so we might see our curve go this way. And then as I go backwards, it's like, again, I kind of get stuck in this current. It kind of pulls me back over here. All right, so these are 3 different solutions to a differential equation that again has infinitely many solutions. And instead really of talking about just the constant, we're going to think of this as always having an initial condition. So these ordered pairs we could think of as an initial condition that must be met for our differential equation. All right, so as we move on to page 122, the actual computer-generated graphs of those three solution curves are presented at the top. And again, there's some really important language on this page. So when we solve the differential equation, we will first find a general solution. And again, that is analogous to finding a general f of x like plus c, when we solve, or rather when we evaluate an indefinite integral. So that's kind of like, well, we don't know what c is. We know that there is this general solution. We just don't know what to plug in to find a constant. But when we plug in our initial condition, that's going to be like our xy ordered pair that allows us to find that specific solution. So that is what we're going to have to do to find C. And we're going to solve these equations in a 4-step process. So first, let's talk about what a separable differential equation is. Not all differential equations are separable. We will only work with separable differential equations in Calc AB. So a separable equation is an equation where the variables can be, well, separated, right? That makes sense, on opposite sides of the equal sign. So we have to be so careful here with our understanding of grouping. That's going to be a big thing to consider because we have to not violate any rules of solving equations, for example. So in this class, we will only solve separable differential equations, but there are lots of math classes where you could solve other types, and I hear that's super fun math. I love solving differential equations, so I think it's a lot of fun. All right, let's just look at this first example. So we are asked to find y equals f of x, the particular solution. So in other words, the specific solution to this differential equation, and then it's going to pass through this point 0, 5. So this is our initial condition, if you ever see that language written out. Okay, so the first thing that we will have to do, step 1, is going to be separation of variables. So if I have dy dx equals x times y, what I can do every time first is multiply by the differential of x, so dx on both sides. And that helps me see that I need all of my y variables on the right, or sorry, on the left where dy is, and my x variables on the right. I always want dy and dx. I do not want 1 over dy. Like, I don't want to divide by dy there. That would be a bad idea. Okay, so I need to get my y variable that's on the right-hand side to the left. And the reason this is a separable differential equation is this is all multiplication. X times y times the differential of x. So I could just divide both sides by y. And so now I could leave it dy over y, or I could write 1 over y dy equals x dx. So that was step 1. Step 1 is separation of variables. In fact, I'm going to write these steps out to the side. So step 1, we're going to separate. All right, step 2, we should be able to do by now is integrate. So the next thing we're going to need to do is integrate. Let me do this in the same line here. I'm going to my next step up here. So when we integrate, we find the antiderivatives. So on the left-hand side, we have the natural log of the absolute value of y. On the right-hand side, we have 1/2 x squared plus c. We must have a plus c when we do this. We don't need a plus c on both sides, though. Think about it. If you write plus c on both sides, you could subtract one constant from the other, and we're just left with a new constant that we don't know what it represents. So we only need a plus c. I always put it on the side with x, and just trust me on that one. It'll be easier. All right, that was step 2. We already did it. If this were the AP exam and this was a free response question, we've earned 2 to 3 points already, so that's pretty exciting. So step 2 is integrate. Steps 3 and 4 can be done in either order. So in step 3 or 4, we're going to solve for c by plugging in the initial condition. I'm going to say use initial condition. And then step 4 is going to be to isolate y. And yes, that is absolutely mandatory. But we can really choose the order we do these in. I usually just try to plug in C first and see what happens, or plug in the initial condition rather. So let's try that. I'm going to plug in 0 for x and 5 for y. So the natural log of 5, I can drop the absolute value since 5 is positive, equals 1/2 0 squared plus c. So the natural log of 5 equals c. Okay, well that was easy. C is just the natural log of 5. So this is very important. When I go back to plug this in, like when we find c, I have to plug it in this exact step, exactly where I was. I cannot manipulate my integration equation anymore, because if I do, c is going to change when I do that. So I got to be really careful there. All right, so I'm going back, and we're going to do that final step where we're actually going to solve this and isolate y. So from this line, I have the natural log of the absolute value of y. I haven't gotten rid of that yet. Oops, I thought I picked a different color. I guess not. Equals 1/2 x squared plus c, the natural log of 5. All right, our goal is to get y by itself. So on the left-hand side, all we could possibly do there is exponentiate both sides. So when we're trying to undo a logarithm, we must do so by exponentiating both sides of the equation with the same base. On the right-hand side, be careful, you're exponentiating, like that entire expression, 1/2 x squared plus ln of 5, that is now an exponent. So this got rid of the natural log. This did not eliminate the absolute value of y. So be careful here. All right, on the right-hand side, we now have e to the 1/2 x squared plus ln of 5 power. And y'all, that might look crazy, but remember our properties of exponents real fast, our properties of powers. Like if I have x cubed times x to the 6th power, I know that means I'm going to add those exponents. So working backwards, if I have a sum of exponents, I could break it down into multiplication. So like here's how that's helpful. We have the absolute value of y equals e to the 1/2 x squared, and write that x squared over 2, times e to the ln of 5. Oh, and we know what that is. E to the natural log of 5, those are inverses. They undo each other. That's just the number 5, you guys. So I'm going to put the 5 right here in front of e to the x squared plus 2. Okay, so this started off really scary. It's getting less scary. How do I get rid of that absolute value symbol? Well, remember, if the absolute value of y is 5e to the x squared over 2 power, that means that y is either positive or negative 5e to the x squared over 2 power. So to get rid of the absolute value, we need to put a plus or minus here. So plus or minus 5e to the x squared over 2. Okay, so we're one step away. So like here's the deal. Which is it? Is it positive 5 or negative 5? My answer cannot be two different equations. We are looking for a particular solution. So what do? We check the initial condition again. Which of those numbers, positive or negative 5, would make my initial condition true? Well, if I want y to be 5, and I'm trying to think, do I want positive or negative? Let's just check positive first. I have a hunch it's going to be positive. This becomes 5 equals 5 times 1, which is positive 5. So we do want the positive here. If I use the negative 5, I would have gotten y equals negative 5. So our final solution to this differential equation, oh my goodness, where did my marker go, is, okay, well, it's the positive one. The screen is not letting me pick a marker anymore. Oh, this is tons of fun. Okay. There we go. I think I had to move that out of the way. I don't know what's happening. But yes, our solution is the positive 5, and we should make sure that we write that down. Oh, I see what happened now. All right. 5e to the x squared. Technology, man. Okay. Let's move on to the next example. All right, example at the bottom of page 122, I think. We're going to, again, find a particular solution to dy dx with the given initial condition. So again, we're going to do those 4 things. We are going to separate, integrate, solve for c, and isolate y. All right, so for that separation step, if dy dx is equal to y squared times x minus 1, again, I could multiply both sides by dx. I never, ever, ever, ever want to divide by dy. That will result in something that will not be correct. And so this helps me see that I need all of my x junk on one side of the equation, and that means I've got to move my y squared to the other. So that's what we mean by separation of variables. And I have to do it with a mathematically viable property, so I'm going to divide both sides of this equation by y squared. Okay, so on the left-hand side, if you do your work all messy like I just did, always make sure you rewrite it 1 over y squared dy equals x minus 1 dx. Okay, so when we go to integrate this, just be cautious. This is not the natural log of the absolute value of y squared. I might want to rewrite that as a power so that I use the power rule. All right, so I'm going to add 1 to my exponent, divide by my new exponent on the right, and then on the left, I get, 1/2 x squared. So add 1 to my exponent, divide, minus 1x. So again, that constant becomes a linear coefficient there. Oh, but I had forgotten something, and right now I would be in so much trouble if I forget. We got to remember that plus c, and we can't think about it later, like we can't tack it on later. AP is pretty picky about that. Okay, so if I rewrite this, I'm looking at this, I have negative 1 over y equals 1/2 x squared minus x plus c. And I'm just looking at this right now. I do not like that negative 1 over y, but I'm going to still try to solve for c or plug in the initial condition first, because if I isolate y first, that initial condition is going to be like stuck in that c value is going to be like in a fraction, and I think it's going to be harder to solve it that way. I have had the advantage of trying this problem both ways before I started making the video. So, all right, so we have done steps 1 and 2. We separated and we integrated. So now I'm going to try to solve for c by plugging in the ordered pair 0, negative 3. So negative 1 over negative 3 is 1/2 times 0 squared minus 0 plus c. Well, that was pretty easy. C is just 1/3. So again, this is really crucial. We have to plug c in exactly where we left, like where we left off to find what c was. We cannot do any other steps with this equation and then plug c in later. So I have to keep this negative 1 over y equals 1/2 x squared minus x plus 1/3. All right, so the last thing we have to do is isolate y. And there's a couple ways, like we could stick a 1 under this expression on the right and solve it like a proportion. Or, I mean, can't we just multiply both sides by y to get rid of our 1 over y on the left? Like, that's our only real problem. So if I multiply by y on the left and right, those parentheses are pretty mandatory. Be careful. I'm going to get negative 1 equals 1/2 x squared minus x plus 1/3, all of that junk times y. Well, now if I want to isolate y, can't I have two factors. I have y times all that other junk. So can I just divide both sides by all that other junk? Yes, we can do that. You know, I'm like, you could probably skip this step where I'm showing my work, but I like to be thorough. So our final solution is y equals negative 1 divided by 1/2 x squared minus x plus 3, or plus 1/3, I mean. And there are ways that we could get rid of those fractions within a fraction. I'm going to just say I'm fine with this answer if you want to leave it like this. Alternately, like if I wanted to get rid of the 1/2 and the 1/3, I could distribute the least common multiple, a 6 on bottom. So we could think of this as like negative 6 over, well, 1/2 times 6 would be 3 x squared 6 times negative x would be minus 6x. And then 1/3 of 6 is 2. So like you can write it this way. I'm fine leaving it the way we had it before. Okay, I'm gonna pause recording on this to start a fresh video on page 123 just because it's getting kind of long. But you definitely should watch them both.